Let's study some global properties of SO3 by looking at an explicit parametrization. So we parameterize SO3 rotation matrices like this. We write Rn, R index n of psi. So that's the rotation by the angle psi about axis n. This is known as axis angle parametrization. And if we use two more angles to specify the axis, spherical coordinates, like this, then we can specify a rotation matrix by three angles. So two angles for the axis and then really one for the rotation angle here. And this is our convention for theta and phi, spherical coordinates. Now, what are the parameter ranges? If we want to allow all directions for n, then we would say theta runs from 0 to pi, and phi runs from 0 to, say, 2 pi, but 2 pi we identify with the 0 again, so it's not equal here. And what about the rotation angle? Well, since we have really, with this choice, the n can move everywhere on a sphere, we have a direction and also the opposite direction. So if we allow for 2 pi rotations for each axis, that would be too much. Then we had each rotation twice. But if we only have rotations from 0 to pi, actually less than or equal to, we need the last one here for the moment, then we have all rotations, but then we still have some redundancies. So with these parameter ranges, we already have all rotations, but some we already hit, we still hit a couple of times. So what are the redundancies here? First of all, if we don't rotate at all, that's the same no matter which axis we choose, let's say. So with angle psi equal to 0, the axis doesn't matter. So these are the identity we have several times here in this parameter range. And then I already hesitated when I wrote down this last line here. So what happens with the rotation about pi? If we take rotation about axis n and rotate by angle pi, then that's the same as taking axis minus n and rotation by the angle pi. But then we have all the redundancies, and now we have to study what SO3 looks like if we take into account these redundancies, so we make some identifications.